Hello everyone, welcome to another video in the FAQ series. Today I'll answer the question, what is reduced takeoff thrust? And more importantly, why don't airliners always take off with maximum thrust setting? So to answer that question, we'll have a quick look at how a jet engine works. We'll have a look at its design limitations and the legal requirements regarding the minimum amount of takeoff thrust. So let's dive straight in and let's have a look at the jet engine. So part of the thrust is being created by the air going through the hot section or the core section of the engine and then leaving at the rear. But the majority of thrust is being created by the cold section, i.e. the fan, which acts just like a propeller. Now, of course, there's also some air going through the core section of the engine. And there, first of all, it is compressed by a low pressure compressor, in this case a 3-stage compressor, then goes into the high pressure compressor, which has in this case 9 stages. It then goes into the combustion chamber where fuel is added and ignited, and then the hot and very fast moving air mass goes through the turbine section of the engine. In this case we have 2 stages, a single stage high pressure turbine and then a 4-stage low pressure turbine. So the turbine section of the engine is connected with the compressor section and the fan assembly. So the rotation of the turbine then drives the compressor and the fan. And so it is obvious that depending on the size of the engine, the materials being used for the engine parts, you have a certain structural design limitation of the engine. In our case here, the pressure can reach up to 300 psi, just past the compressor. And the temperatures can reach, well, in excess of 1500 degrees Celsius, depending on the engine type, which is of course then reached just past the combustion chamber. So very simply put, the faster the rotation of the engine, the more thrust will be created. However, also the pressure will increase, temperatures will increase, and cause more stress on these parts of the engine. Through thorough testing, the engine manufacturer will then determine the maximum allowable thrust rating for its engine. The engine manufacturer will publish a maximum takeoff thrust setting, a maximum climb thrust setting, maximum cruise thrust setting, and also a maximum continuous thrust setting. Of course, this video is about the takeoff thrust setting, so let's concentrate on that. So let's first assume that the engine is running at its highest possible RPM, i.e. the design limitation of the engine. Then as the outside temperature increases, the density naturally will decrease, and that will also decrease the thrust. And so this is called a full rated engine. On the bigger jets, however, you will now these days find the so-called flat rated engines. So what does that mean? It simply means that up to the so-called flat rated temperature, the thrust is limited electronically by the electronic engine control unit. And so you can say that up to the flat rated temperature, the thrust is being kept constant, and that is for mechanical limitation reasons, i.e. the maximum allowable pressure in the compressor area, or to prevent a stall of the airflow going through the engine. So a big advantage is that up to the flat rated temperature, you will have a constant thrust output, and so there's no need for extra structural strengthening due to higher pressure and thrust outputs caused by higher density, either through colder temperatures or lower altitudes. Be aware that different engines have different flat rated temperatures. For example, you will come across quite often a temperature of around about 30 degrees Celsius, i.e. Acer temperature plus 15 degrees. However, in the FS Labs, for example, the CFM engine there is flat rated at 44 degrees Celsius. So the characteristic of the engines are as follows. As the outside temperature increases, the output thrust will be the same by increasing the RPM of the engine. That is being achieved by obviously injecting more fuel into the combustion chamber. and hence you have unison increase in N1 and also in EGT up to the point where it reaches the flat rated temperature. At that point, you have reached the maximum allowable EGT. Here we are again at the structural limit. And at that point, obviously, as the outside temperature rises even more, you're going to have to limit the amount of fuel being injected into the combustion chamber. And hence, the N1 will start to drop. And that means also, of course, that the thrust will decrease from that point onwards. So let's demonstrate this here in the FS Labs. You can see that as the outside air temperature is increasing, and by the way, we're on the ground, we can say that the air density is decreasing. And so the N1 has to be increased in order to achieve the same thrust output. And again, we're talking about a flat rated engine here. And as mentioned before, the flat rated temperature of the CFM engine here is 44 degrees Celsius. So let's now watch how the N1 continues to increase up to the point where the outside air temperature reaches 44 degrees. And then once it goes beyond that, you will see the N1 in percent starting to drop again. So 93.4% is the highest value that we've achieved here. We're now at 47 degrees outside temperature. Now you can see the N1 is dropping. And that is because the maximum allowable EGT has been reached once we set the Toga power at these outside temperatures. And so the FARDEC or the EEC control, the engine electronic control, will start to reduce the fuel flow in order to stay within these EGT limits. Let's have a look at the Boeing 737 here. And remember, this one is flat rated at 30 degrees Celsius. So we can see the outside temperature now starting to increase. And so the N1 has to be increased as well in order to achieve the same thrust output. Now we are about to reach 30 degrees Celsius and the peak value of 100.3% on the N1. And now going past the flat rated temperature, we can see the EEC has to limit the fuel injection, i.e. the N1 is starting to drop again, and also the thrust will decrease. So we can see that the flat rated temperatures are quite different comparing the A320 CFM to the Boeing CFM engine. So obviously these engines will be priced differently, and it's up to the operator to then decide which of these kind of envelopes is best suited for them, and that will obviously have to do with the region that these aircraft will operate in. As a little side note here, the operational EGT limit is obviously well below the design EGT limit, and that has to do with the fact that as the engine deteriorates with age, it will need an increased fuel flow and hence a high EGT in order to produce the same required takeoff thrust. And over time, the EGT margin will therefore decrease and eventually will reach its design EGT limit, at which point the engine will have to be removed for maintenance. Another thing I want to point out here is for the engines that are using EPR indication, i.e. engine pressure ratio indication, showing the difference between the inlet pressure and the outlet pressure of the engine. And the advantage of that indication is that it actually shows the true thrust output. And so when the outside air temperature is rising and the electronic engine control is having to inject more fuel to achieve the same thrust output, contrary to the N1 increasing, the EPR ratio will actually remain constant. Here we are again in the FS Labs. On top you can see the Toga setting in EPR, so 1.393. On the bottom you can see the outside air temperature. And now just have a look how the increase in outside air temperature actually does not affect the EPR ratio. Now also keep an eye on the indicated EGT value here as the outside air temperature increases. Demonstrates quite nicely how to maintain the same thrust setting you have to increase fuel flow, increase the RPM, and that increases the EGT. We're now reaching 30 degrees Celsius, EPR still at 1.393. So let's go up to the flat rated temperature at 44 degrees Celsius. And then let's see what happens. There we go. Now we can see the EPR decreasing again quite drastically as the temperature goes beyond 44 degrees Celsius. And so a drop in EPR means a drop in thrust. And again, that is because we have reached the EGT limit of the engine, and now the electronic engine control has to decrease the fuel flow to remain within the EGT limits. So let's now finally talk about why we do reduced thrust takeoffs. So you have to understand that the engines are designed to be strong enough to produce the required amount of thrust to allow the aircraft to take off and climb out at the maximum certified takeoff weight. Assuming, for example, an engine failure after V1, and this from airfields that don't have a very long runway or that are at higher elevations or in unfavorable weather conditions like hot temperatures. And of course, it doesn't happen that often that the aircraft will be taken off at the maximum structural takeoff weight, or that environmental conditions are so extreme, for example, very hot temperatures, that the aircraft just simply cannot depart at its maximum structural weight. So you can say that whenever the actual gross weight of the aircraft is below the limited gross weight, so either because of runway length or climate limitations, there is no need to use maximum available thrust. It's just like in a car where you don't always, put the pedal to the metal, as they say, and go full throttle. There's simply no need to do so. And so pilots these days have computer programs. I remember my earlier days of flying, we had paper charts or paper tables where we would calculate the reduced thrust settings. Some aircraft use fixed D-rate values. I'll get to that in a minute. But like I said, pilots have means to calculate the required amount of thrust for takeoff. So the benefits from this are, of course, a lower fuel flow and hence a lower EGT, exhaust gas temperatures for takeoff. That means a lower fuel burn. Also fewer operational events due to high EGT. Lower probability of an engine failure, since lower EGT means less engine stress. And then, of course, lower maintenance costs, since the EGT margin over time will decrease slower, and thus extending the so-called life-on-wing time span. Now, there are two main methods of determining a reduced thrust for takeoff. One is the assumed temperature, or also called flex temperature method, and the other one is a derated thrust method. Although the derated thrust method can also be then combined with the assumed or flex temperature. Let us now have a look at the theory of flex temperature calculation. Now, this graph is valid for a specific airport runway with given environmental conditions. So if you have a different airport runway, or if conditions change, i.e. temperature decreases or increases, pressure drops or rises, etc., then these graphs will change as well. So the blue line represents the maximum available thrust. So the maximum thrust the engine can produce under these given conditions. And so this engine here is flat rated at 30 degrees Celsius. And that means once the outside air temperature at the airport increases above 30 degrees Celsius, then the maximum thrust will start to be reduced. The magenta line, on the other hand, shows the maximum possible takeoff weight given the actual runway and the environmental conditions, and given the maximum thrust setting possible. And that means all cases regarding field length, climb gradient, and obstacle clearance are being met by this max takeoff weight consideration. And you'll notice already that even though the thrust output of the engine remains constant until the flat rated temperature of 30 degrees, the maximum possible takeoff weight starts decreasing already. And that is due to the decrease in density of the air and hence the aerodynamic implications that it brings. Now, once temperatures rise above the flat rated temperature, as the thrust is then decreased, then of course the maximum takeoff weight will reduce rather drastically. So in this example, we have an actual outside air temperature of 23 degrees Celsius. Now, looking at the magenta and the blue graph there, we can see the max thrust is available, and that means a given maximum takeoff weight at 23 degrees Celsius is being given. As mentioned before, it's very rare that you are at the maximum takeoff weight with the current gross weight of the aircraft. And so in this example, the actual takeoff weight, represented here by the green lines, is a lot lower. And so we can say that we have excess thrust available, so thrust that is not really needed. And that gives us now the option to use the assumed temperature method to reduce the thrust in order to save fuel, have lower EGTs, etc., etc. So now all we do is go to the right with the actual takeoff weight until we hit the maximum takeoff weight magenta line. And that intersection point will now give us a certain assumed temperature, in this case 62 degrees Celsius. So going back to the maximum takeoff value point on the chart here, and then go straight up until it meets the maximum thrust available line, will then give us the required thrust setting for the assumed flex temperature of 62 degrees Celsius. Luckily these days pilots have software programs available to them to work out these required thrust settings for them. Something very important to mention is the fact that the thrust reduction is limited. In most cases, it is limited to 25% of the maximum thrust value. And so you can imagine that flex temperature or assumed temperature is engine type related. And in this example here, you can see that the actual takeoff weight is so low that you could theoretically flex even more. However, again, because you are then reducing by more than 25% from the maximum thrust value, this is not allowed. I'd like to do one more example. In this case, we have a very hot day. So the actual outside air temperature is 40 degrees Celsius. And so the question is it still worth to use flex temperature in this case? Well, we can see the actual takeoff weight is only slightly below the max takeoff weight value, and hence the thrust required for the assumed temperature of 46 degrees in this case is a little bit below the max thrust available for the current outside air temperature. So that difference is fairly small, meaning that the advantages with the reduced thrust setting here is also very, very marginal. One last point to make here is that obviously it does not make sense to use assumed temperature method below the flat rated temperature. And that's simply, as you can see from the chart, that you will be selecting max takeoff thrust all the time. So let's have a look what the difference is between a toga power setting and a flex temperature setting here in DFS Labs on takeoff. So we can see toga power says 91% N1, the flex takeoff power says 87.8%. So quite a good reduction in the N1, and that correlates to a flex temperature of 55 degrees. And the temperature difference of the EGT is round about, well, we can say almost 20 degrees Celsius. And the fuel flow is about 250, 260 kilograms per hour. Assuming that it takes about 3 minutes from the start of the takeoff run until you reach climb or thrust reduction altitude to reduce the climb power. The savings aren't that great. I mean, anywhere between 15 to 20 kilogram per engine. But nonetheless, if you consider all takeoffs, all the aircraft, especially when the airline has many aircraft in their fleet, throughout the year, the savings are actually quite substantial. On top of that, of course, due to the lower EGT values, as we have mentioned before, you do save on maintenance costs as well. Now let's have a look at the derated thrust method. And for this, we'll pull up another chart. And here on the left scale, you can see the takeoff weight values, and the lower one is again the outside air temperature. So derated thrust is simply a fixed percentage value of thrust below the max rated thrust. So in these instances here, we have minus 10% or minus 20%. Quite often those would be called TO1 and TO2. So in this chart, anywhere on the red line there showing max rated thrust, you can see the corresponding maximum takeoff weight. And of course that for a given outside air temperature. In this very example, we can see the actual temperature is, let's say, 25 degrees Celsius. And we have an actual takeoff weight. We can see the thrust required is somewhere in between minus 10 and minus 20% derated thrust. So obviously we cannot take minus 20 degrees derated thrust, because in that case we would not have enough thrust available for the given takeoff weight. The max rated thrust would obviously put us in a position where we have a lot of excess thrust. So in this example we would take the minus 10% derated thrust. It still gives us excess thrust, but not as much. And as mentioned before, there is a combination of this derated thrust method and the assumed or flex temperature method to kind of fine-tune the amount of derated thrust. Either way, be it just a simple assumed flex temperature calculations or the derated thrust method, it all leads to the same effect, and that is to reduce the fuel flow, reduce EGT, increase engine life, decrease maintenance cost, and so on. So here to give an example, we have the PMDG 747, and I have selected takeoff 1, departing out of Luxembourg, runway 06. It gives us flaps 20 for the given takeoff weight, and not just takeoff 1, but also a selected temperature of 38 degrees Celsius. And that's what I mean with a combination of derate, takeoff 1, but also a assumed temperature of 38 degrees Celsius. So how would we know whether or not we can take takeoff 2? Well, just simply select it, calculate it, and there we go. It says no valid assumed temperature found for these conditions. And so then you would try takeoff 1. If you get the same message again, well, then go with full takeoff thrust. The good thing is a lot of add-ons these days come out with a integrated takeoff performance module, be it in the EFB or in the MCDU, like here in the FS Labs. Otherwise, there is other software out there. Sometimes you can use TopCat, for example, or maybe you can find a calculator online on the internet. Okay, we have reached the end of the video. Thank you so much for watching. Thank you to everyone who's supporting me, especially on Twitch. And so to everyone, stay safe, keep positive, and I'll see you in the next video. Until then, happy landings.